Thank you for having me. Special thanks also to the organizers. I will talk a little bit about making mainstream programming languages deterministic again. This is actually a work that is a product of a collaboration between wonderful people at Berkeley, UT Dallas, TU Dresden, and also the University of Kiel.
Martin, I'm still not seeing your screen. Does anybody else see it yet?
I see it on the.
It's fine for me.
I
do see the screen.
Okay, it's just me.
Well, if the slides travel from California to Europe, they must pass somewhere around New York.
Yeah. Well, maybe they go first to France and then come back with a delay. We'll see. Okay. Well, it's hard to overstate the success of deterministic models. Examples are synchronous digital logic, instruction set architectures, and sequential software, just to name a few. The reason for the success of deterministic models is that they're easier to test, their correctness and safety is easier to verify, and the simulation of those kinds of systems is more practical. But what exactly do we mean by a deterministic model? It simply means that given the initial state and the inputs, the model defines exactly one behavior. I just wanted to quickly show this definition so that we're all on the same page. We'll get back to it a couple times throughout this talk. So achieving determinism has been a goal in the development of synchronous languages, mostly targeted at real-time control software. They're known for allowing programmers to write modular and mathematically precise system specifications, to simulate, to verify them, and ultimately to also translate them into embedded code. Very well known, of course, are Signal, Esterel, and Lustre. And a notable success also is SCADE, because it's been applied in safety-critical software in nuclear power plants, aeronautics, and railway systems. And the work I will present today also has a clear connection with the sparse synchronous model presented by Stephen Edwards yesterday. And the notion of sparse synchrony actually fits our model very well. We also leverage the sequential constructiveness idea from SE charts. We increasingly need parallelism in our computing platforms to achieve performance goals. To scale with big problem sizes, to accommodate highly variant workloads, to deal with the inherent complexity of the systems that we build. In cyber-physical systems, which are intrinsically concurrent, of course, because they interact with the physical environment, there's an interesting tension that has arisen. Where we used to think of them as highly specialized, embedded, resource-constrained, we now see them become integrated with resource-hungry AI systems, for example. Think of autonomous driving. And these require very powerful hardware and even access to the cloud. And yet, the parallel and distributed computing community has, in a sense, turned its back on determinism long ago, with prevailing paradigms including actors, publish, subscribe, server-oriented architectures, where everything is asynchronous. And of course, asynchrony is also good for latency hiding and useful for avoiding deadlocks, but the loss of determinism is troubling. Especially when these technologies make their appearance in safety-critical systems. And these days, people are building systems in ROS and AutoSAR, and they're caught by surprise when they encounter non-determinism. Last year, actually, I co-authored a paper specifically on this topic with my colleague Christian Menard at TU Dresden, and there we took a demonstrator application of the newly proposed AutoSAR AP framework, an automated braking system, actually, and we showed just how badly non-deterministic it was. So the focus of our work is to reclaim determinism in these sorts of systems. And as is the case for synchronous languages, our solution involves leveraging some semantic notion of time. So reactors are based on an interesting mix of ingredients from synchronous languages, from actors, object-oriented design, also discrete event systems, distributed systems, and even hardware description languages. In a way, we're following Tony Hoare's advice to prioritize consolidation of good ideas over the proliferation of new ones. Of course, there are some novelties in reactors, but we'll get to those later. Synchronous languages are not winning the popularity contest, but in all fairness, most languages aren't. Depending on who you ask, there exist hundreds or even thousands of them. And there are a lot of things that factor into the popularity of programming languages. But in any case, it's certain that it's not easy to create a new language and make it popular. It is extremely difficult to convince individuals, companies, communities to abandon languages that have become invested in. The costs are simply too high. With reactors, we saw an opportunity to bring synchronous reactive principles to a larger community, not by creating our own language and to compete with these giants, but to create a coordination layer that can exist symbiotically with these existing languages. And we implemented this coordination layer in the form of a language we call lingua franca, or LF in short. Programs written in LF compile down to several different target language, including C, C++, TypeScript, and recently also Python. The data dependencies are explicit in our model, and the execution of an LF program follows a discrete event semantics. Reactions to events are logically instantaneous, and the logic inside of reactions is given in verbatim target code. So in the slide, you can see the top portion is C code. Then below that, you see the composition of reactors written in lingua franca. And we also have a feature in our IDE that was developed by Alexander Schultz-Rosengarten that is very nice interactive rendering of the program. So you can actually navigate the code by clicking on elements in the diagram. You can hide details or magnify them. That's been really helpful for understanding code and for explaining what it does. So here's an overview of the compilation process of a lingua franca program. So the program goes in, it gets parsed and validated. Then if there are any syntax errors in it or any semantic errors in it, they will be reported. But of course, because the reactions themselves are written in target code, we don't fully know yet whether there are any problems in the program. We first need to send it to the target compiler and let that compile our generated code. Then if there are errors in that, that will also be fed back to the lingua franca programmer. Finally, if depending on whether it's an interpreted program or a compiled program, it either goes directly to the interpreter or gets compiled and turns into an executable. So there are some aspects of lingua franca that are novel. One of them is the capability of relating events across different timelines. And among those timelines, we distinguish two different kinds, logical ones and physical ones. So what do I mean by that? As in synchronous languages, logical time progresses with discrete ticks and no sooner than the work for that time step has completed. Physical time, on the other hand, increments continuously, and two subsequent measurements of physical time, given sufficient resolution, of course, will always differ from one another. But the picture is a little bit more complicated in the physical case because simultaneity is actually a relativistic notion in physics, meaning that it depends on the frame of reference of the observer. And this makes it not very practical as an abstraction for engineering systems. In logical time, on the other hand, simultaneity is an absolute predicate, making it much easier to reason about. But we can't just stick with logical time. If we care about the interactions with our environment, we may want to react to stimuli from the environment, for instance. What time should we associate with those? We may want to impose deadlines to ensure that our computational system can keep up with its physical counterpart. Or we may want to define system behavior that spans locations that are physically distributed. We also might want to respond when our assumptions about timing of events in the physical world is broken. And all of these things require to relate things across timelines. And in lingua franca, we provide abstractions for that. So as I already mentioned, lingua franca is based on reactors. And to understand LF, we first need to understand reactors. So let me briefly walk you through some of the key aspects of reactors and their execution semantics. Reactors have ports. Values are written to ports, and they constitute events that can trigger reactions. Reactions are totally ordered within the reactor that contains them. If two reactions within the same reactor are executed simultaneously, their order of declaration determines which one executes first. Reactions need to explicitly declare the ports that they access, or if they don't, a compilation error will occur. And reactions can also be triggered by a special trigger called startup. This is presented by the bullet, which is only present at the first instant of each reactor's life cycle. Similarly, we have a shutdown trigger. It's the lattice shape that is only present at the last instant of the reactor's life cycle. An event at one port can trigger more than one reaction. Not all reactions are triggered at every time step, so this is indeed a sparse model. And following the sequential constructive principle known from SC charts, when two reactions get the value of the same port, only the last written value survives, and no downstream reaction is triggered before the value has settled. Reactors can also be contained in another reactor, and the container can also itself have reactions. And within the scope of the containing reactor, ports can be connected. Cycles in the connection topology are permitted as long as they don't introduce any cyclic dependency between reactions. So this connection is totally fine. Now let's go through a simple execution run. The startup trigger, the startup action triggers the first reaction of A. And let's assume a value is produced in the first reaction of A, which then triggers the second and third reaction in A. If either or both produce a value, this triggers the second reaction in B and the first reaction in C. Note that these two reactions have no ordering or data dependency between them, so they can execute in parallel. After all of this, we're still at the first time instant, and there are no more reactions to be triggered. So we're stuck. How do we advance time and where to? For this, we need the logical action that is indicated with the arrow here. The first time that this action triggers reaction 3 of A, the other two reactions are not triggered because startup is absent. And then the second reaction of B and the first reaction of C will be triggered again. And now we've reached the end of a tick, and the program will just continue to react like this every 20 milliseconds. And finally, if if a timeout was specified or a shutdown was requested in one of the reactions, the last reaction of B is triggered. So now let's look at some lingua franca code. This code specifies a main reactor with 3 contained reactors and connections between them. A timeout of 1 second has been specified, so this program only runs for 1 second. And we also have a shorthand notation for the periodically scheduled logical action that we saw on the previous slide, and we call these timers. This particular timer has no offset and a period of 100 milliseconds. Logical actions can also be used to specify logical delays between reactions of different reactors. And the delay here uses a logical action that has a 50 millisecond delay. So here's the output of our simple program. We first compile it with LFC, which generates C code, then includes a runtime, and it compiles it with GCC. We then execute the binary, and as expected, the printed time values start with an offset of 50 milliseconds due to the initial delay, and then continue with a period of 100 milliseconds due to the timer. And notice that the elapsed logical times are exact. So the physical times, they approximate the specified timing. And this is because in lingua franca, events are not released until the physical time has surpassed their tag. Of course, if so desired, physical times can match the logical times much closer when this code is executed on hardware that admits better control over timing, such as FlexBread or Patmos. This particular run was just done on my laptop. And because logical delays are of common use, we also provide a shorthand syntax for those. The LF compiler carries out an AST transformation, actually, that wires each connection with an after through a kind of delay reactor that we saw in the previous example. So now let's discuss physical actions. Consider the following simple cyber-physical system with a sensor, a controller that performs some analysis, and an actuator. When the sensor starts up, it creates a thread that monitors the keyboard. It's basically the only portable sensor that we have to our disposal, right? So it passes along a reference to its physical action called response, so that read input can schedule a response whenever a keystroke event was detected. And since this happens asynchronously in a separate thread, there will be no well-defined logical time relative to which the response action can be scheduled. And instead, the resulting event will acquire its tag from the physical clock. And that is what sets logical actions apart from physical actions. So when you schedule a physical action, you get the measurement of the physical time. When you schedule a logical action, you get the last known, you schedule relative to the last known logical time. Now, this business with physical actions, you might think this spells trouble because, we're introducing a source of non-determinism. And that's true, but let's have a look at our definition of determinism again. So we have to keep in mind that the events scheduled on a physical action are derived from a measurement of physical time. And therefore, they are inputs to the system, just like the values associated with those events. And the system reacts deterministically to those inputs. And the outcome of the further processing, assuming that the reactions themselves, of course, are not a source of determinism, is exclusively determined by those inputs. So our coordination itself does not introduce non-determinism. So let's have a look at what the rest of our program does. We also have an analysis reactor that is triggered by our sensor, and rather than doing actual work, this guy just invokes nanosleep. But it only does so every other triggering. So the first time it gets triggered, it sets output Y immediately, and the second time it spends 500 microseconds of physical time, and so forth. So finally, our actuator prints out to standard out, and it also specifies a deadline. This is a predicate that gets evaluated once the actuator's reaction has been triggered and is ready to execute. This determines whether the reaction will execute or whether the accompanying deadline mishandler in the subsequent code block is executed. So there are two code blocks here. The first code block is the normal reaction, and the second code block is the deadline mishandler. Recall, at this point, the current logical time is still equal to the tag that was assigned in the sensor based on the physical clock. And no logical time has elapsed during the preceding reactions that have executed during the same tick. So the predicate is as follows. If the current logical time plus the deadline of 500 microseconds is greater than the current physical time, then the reaction is considered on time and it just executes. If the opposite is true, then the execution is lagging behind physical time by more than 500 microseconds, then the alternate reaction is executed. Now, with an analysis component that does actual work and an actuator that needs to respond within a bounded amount of time, such as in an emergency braking system, we need to estimate the worst case execution time in order to make sure that the deadline doesn't get violated. But we still have a mechanism to catch it when it happens at runtime. So we can have a look at what our little test program does here. We actually have a number of examples in our repository that you can check out and use. I will check this one in too. So here, we see an interleaving of reach deadlines and missed deadlines because of the behavior of our analysis component that waits for wall clock time to pass, and therefore causes a deadline miss.
5 minutes.
Okay. So the point here is that the non-determinism stems from factors outside of the semantics of LF. Deadline reactions should be considered fault handlers, and the assumptions on physical execution. And if the assumptions on physical execution time are met, the system behaves deterministically. And for the case where they don't, then the runtime error handling mechanism is available to address the fault. So here's another example that might be familiar to some of you. It is also checked into our repository. This is a simple reflex game. I don't think I'll have time to go over the code with you, but it's actually a very compact example. The random source prints on standard out with some random interval. It notifies the get input component that it did so, at which point the get user input makes a record of the current physical time, and then whenever the user presses the key, a physical action gets scheduled. The second reaction of get user input gets triggered, and it prints the delay. And you can see there, the response time, about 300 milliseconds is normal for a human. I also cheated by, I guess, guessing, and there I got 52 milliseconds. That's not what you usually get. If you, however, hit the enter key before something was printed, it obviously detects that you were cheating and tells you so. In LF, it's also possible to specify what's called a federated program, and this allows for reactors to be mapped to different hosts. So just like the after keyword, as we discussed earlier, an AST transformation substitutes connections between federates with functionality that handles the sending and receiving of messages through the network. The LF code generator generates separate binaries in a shell script, and when that is invoked, the respective hosts, they connect and start a distributed execution. And of course, if we distribute our reactors among different compute platforms, then we no longer have 2 timelines to deal with. We have a multiplicity of them. And of course, with this many observers, physics gets into the way of knowing what the true order of events should be, but we could still preserve our discrete event semantics if we ensure that each observer sees all events in timestamp order. And you might think, well, you can use TCP/IP for that, but that doesn't work if you have a topology that has branching in it, because TCP/IP only provides in-order guarantees between two endpoints. So if we choose a centralized coordination, then we have a central entity that is also co-generated from the program, through which all the messages flow, and it controls the advancement of time. I won't go into the details of that, but of course this can form a performance bottleneck, and it also becomes a single point of failure. Perhaps more interesting is our fully distributed coordination model, in which each federate controls its own advancement of time. And the question here remains, of course, how to ensure that all events are observed in tag order. And this question boils down to the following question. Given a tag T, how much physical time should be allowed for reordering incoming messages from other federates, such that so that after this time window, we can expect no more messages to arrive with a tag smaller than T. So you can see here this window in the figure. We have X and Z. X happens before Z, but it arrives out of order at the receiver baz. And if we allow sufficient amount of time, we'll receive both, and we can process them in reverse order so that they're ordered properly again. So the question of how to do this has been answered in previous work, and it's called TIDES. It's similar to Google Spanner, and it requires knowledge of the connection topology, which in reactors we have, bounds on the execution times, which are arguably easier to compute for reactors because they're small, broken down snippets of code, network latency, and also clock synchronization error. And of course, since every message is a tag, it will also be detectable when messages are received that are out of order and arrive too late outside of that window. And then we know that one or more of our assumptions with regard to these bounds have actually been broken. To summarize, lingua franca provides an opportunity to augment mainstream programming languages with deterministic concurrency based on synchronous reactive principles. We make time a first-class citizen in the language, something that mainstream programming languages also don't have. We have a scheduler that can handle not just periodic task models, but can also integrate well with events that come from the environment and cater deterministic responses to those sporadic events. And we also have deadlines. These deadlines are used, on the one hand, to inform the scheduler, and to actually our C implementation implements an early use deadline first schedule. And secondary, it gives you an error handling mechanism. And then lastly, and this is, I guess, somewhat similar to the hip hop idea that we saw earlier today, where both the client and the server are in one program. Here too, you write a federated program as one program, and then that gets distributed to multiple hosts. I'd also like to show this slide. We're lucky to work with a group of very talented people that are all putting their time into lingua franca, and I wanted to make sure to acknowledge them before we open up for questions. Yeah, that was it.
Thank you, Martin. So we have time left for some questions. There is a question of Renard on Slack. Okay, so I will read it. So he asks if you could elaborate a bit more on the handling of concurrent and distributed timers.
Concurrent and distributed timers.
Mm-hmm.
Okay, so the timer is basically a logical action with a reaction that goes in a loop, right? So when the reaction occurs, then it has to reschedule itself, and we provide syntactic sugar for that. So that way we can produce periodic behaviors. In a distributed setting, depending on whether you're talking about the distributed coordination or the centralized coordination, in the centralized coordination, whenever you want to pull events from the event queue, first of all, you have to wait for physical time to have surpassed the tag of the event that you want to handle. And then secondly, you also have to ask the central coordinator, can I actually advance to this tag or not? In the distributed case, the distributed coordination case, you don't have to ask that. You only have to watch your own physical clock. And this is where the safety process analysis comes in, because there it's no longer sufficient to wait for physical time to be larger than the tag that you're interested in handling. You have to also add slack for the safety process, for this reordering that might have to be done because of messages that come in from other federates. But generally, the idea of waiting for physical time is to make sure that if you have any things happening in the environment, any physical actions, because they will always acquire a timestamp from the current physical time, then you have to make sure that those things don't end up in the past, right? You want to still be able to handle them and not break this principle of handling all events in order.
Triggered architectures and all
Oh,
that.
right.
Like,
Yes. I don't remember if I discussed this with Edward at PLBI, but maybe you will answer me. A very interesting way to handle time is used by Google in the Spanner database, which is
Yes,
which uses the, because on the internet you have NTP basically, or maybe other systems which are not very precise but not bad, and so Spanner uses interval of time that grow over time between synchronization periods, and I think that's a smart solution which has been studied extensively by them. Do you think of using this kind of thing for Lingua Franca as well, or is it too complicated for your needs?
No, it's exactly what we're doing. This is the distributed coordination that I mentioned. So I'm citing tides. Actually, this technology was invented independently around the same time by people in Edward Lee's research group, as well as people at Google. And Google had in mind to use this for as a consistency mechanism for their distributed databases, and more people are aware of it. But yeah, this is exactly the principle that we use.
Okay.
And it is the fact that reactors have time encoded in it, principally in the model, not just logical time, but also having access to a physical clock, makes it that it's almost tailor-made to work with that.
It shows once again that a synchronizing clock is a key thing to simplify systems compared to distributed programming. Synchronizing clock is not too hard and it's extraordinarily useful. Okay, thanks.
I agree, yeah.
Thanks for the answer.
Thanks for the question.
Other questions? No? Okay, so thank you again.